So the very end, this is the last session of this conference. We have two talks. The first one is by Yizheng Zhu on the higher sharp.
Okay, so is the sound okay? So before I start, I would like to thank the organizers for giving me a chance to talk in this great conference. So the title is The Higher Sharp. So the point of this talk is is an attempt to get a better understanding of the set of reals. And so we are trying to understand, in particular, the subsets of reals of different complexities. So at the bottom of the complexity hierarchy are the projective sets. So in our talk, the set of reals is the bare space, it's the infinite strings of natural numbers, so that product spaces will be homeomorphic to the one-dimensional. And a set of reals is sigma 1n, light phase, means it's sigma 1n definable over the structure v omega plus 1. And it relativizes to a real number. And its bold phase sigma 1n means it's light phase, it's sigma 1n relative to some real number. Or equivalently, sigma 1 means it's the projection of a closed set bold phase. So is there a laser pointer? So I use sigma 1 if there's a closed set, so that if there's a closed set, two-dimensional set whose projection to one dimension is sigma 1. And pi 1n means the complement being sigma 1n, and sigma 1n plus 1 is the projection of the one level below. So the class of projective sets are just the sigma 1n sets for some number n, which means, well, you think of taking a closed set and taking the projection and complement and projection again, doing it finitely many times. The closure of those operations will be the projective sets. So these are the relatively simple defined sets of reals. And the reason why we study this is, well, they are relatively simple. They are definable. So for instance, well, we know there is the big non-measurable set, but the proof heavily uses the axiom of choice. Even DC is not enough. So it's obvious that, well, the big non-measurable set should not be easily definable. And this intuition is validated by the axiom of projective determinacy. So every projective set is the big measurable, and they have other regularity properties like the Baire property, or the effective continuum hypothesis, which says if a set of reals is uncountable, it must be equinumerous with a whole set of reals via a projective bijection, or it actually contains a perfect subset. So for instance, well, the continuum hypothesis is a very vague question in normal mathematicians' points of view, because they seldom quantify over all subsets of reals. They usually only look at the effectively definable sets of reals, and in that sense, the projective version of CH is true, assuming the projective determinacy axiom. And the PD is proved by large cardinals, so it's quite surprising that the large cardinals or higher forms of infinity has such a strong influence on the set of reals which sit at the very bottom of the V hierarchy. So yeah, this is a very beautiful theorem. It's very surprising that something higher up has influence on the sets of reals. So it says, assuming large cardinals, we will get certain levels of projective sets are determined. Assuming there are infinitely many wooden cardinals below a measurable, then all sets of reals in L of R is determined. And well, in this talk, it does no harm to assume proper class many wooden cardinals, so that every subset of reals in L of R is universally bare and is determined. So the regularity properties are usually in those theorems exhibited by the tree representation. So this is quite familiar to descriptive set theorists. So a tree on omega times a set is a subset of finite strings, and the two coordinates have this equal length and closed under initial segments. And for a tree, the collection of infinite paths is the set of infinite strings, x and alpha vector, so that every initial segment belongs to the finite part. And the projection of T is the set of reals, so that there is an alpha in the second coordinate, so that x alpha belongs to the, this is infinite branches of T. So a set of reals is lambda Suslin if it's of the form of projection of a tree on omega times lambda, where lambda is an ordinal, and its Suslin means it's lambda Suslin for some ordinal. So sigma 1 sets are omega Suslin. This can be taken as one of the definitions of bold-face sigma 1, and light-face sigma 1 sets, they are omega Suslin, and the tree that projects to the light-face sigma 1 set is effective. So this is the effective version of Suslinis. Well, we know that the axiom of choice is true in the universe, so every subset of reals is Suslin. But the trouble is the proof of this is relies on ordering of the reals. So the Suslinis of every subset of reals, so the tree is not that easily defined. It depends on the axiom of choice. And as mathematicians, we would like to see, well, how effective can the Suslinis be? So a typical way of testing the effectiveness of the Suslin representation is by looking at the basis theorems. So it says, well, a certain uncountable subset of reals must have a member, and how complicated must the member be? So we can think of a mathematical property about the reals. If this property is not Faker's, well, it must have a member, and how complicated is it to find a witness to this property? So at the sigma 1 level, this is Kleini's basis theorem. Every non-empty sigma 1 set contains a real recursive in Kleini's O. And for sigma 1-2 sets, if a sigma 1-2 property about the reals is non-empty, it must contain a real which is delta 1-2 when coded as a subset of omega. And assuming large cardinals in the background, every non-empty sigma 1-3 set contains a real which is recursive in the mouse M1 sharp. And this M1 sharp is the minimum mouse with a sharp above a wooden cardinal, so the proof uses wooden genericity iteration. And after all, so these are the optimal basis theorems one might get. So we just talked about the Suslin representations. So the way of looking at this is, well, the trees must be easily defined so that the leftmost branch should be not that hard to define. So, well, let's say we have a set of a certain complexity which is non-empty and it's Susselin. Well, we define that we define the leftmost branch, x alpha. Well, it's the leftmost branch if for every infinite branch the order this infinite string x0 alpha 0 x1 alpha 1 is lexicographically smaller than y0 beta 0 y1 beta 1, so it's the leftmost path. And well, it has two coordinates, so the first coordinate of the leftmost branch is called the leftmost real. So it's the leftmost real associated to T. So all those basis theorems can be proved by this descriptive set theoretical way of thinking. It's Susselin, and we look for the leftmost real. Well, the trees are easily defined so that by analyzing the complexity of the trees, we get the complexity of the reals coming out of the basis theorems. Well, just now I mentioned sigma 1 sets are omega Susselin, and well, assuming, well, just still under ZFC, well, climbing one level up, sigma 1 2 sets, they are omega 1 Susselin, but they are very effective in the sense that it's the Schoenfield, the Schoenfield tree. So the way we look at it, sigma 1 2 sets is it's the projection of a tree on omega times omega 1, while the second coordinate is easily computed. And so the second coordinate is on omega 1, and we have a very natural way of coding ordinals up to omega 1, which are the countable ordinals. That is, we code a countable ordinal by the set WO, which consists of reals that codes a well ordering of omega. So every infinite countable ordinal is coded by a real number, and the set of codes is power 1. So the natural question is, well, how far can we get beyond sigma 1 2? So what about sigma 1 3 sets? What is the optimal complexity of the Susselin representation for sigma 1 3 sets? And in general, well, we would like to get we would like to code an arbitrary ordinal smaller than the wage ordinal of the Universität Bär sets. So the next level is the sigma 1 3 sets, and assuming large cardinals, in this case sharps for reals, they are effectively U omega Susselin, where this is the omega uniform indiscernible. So I'm going to introduce the definition of U omega. So we have to assume large cardinals, and so the U omega, or the Susselin representation of sigma 1 3, relies on the sharp representation of relies on the definition of the sharps. So assume large cardinals, there is a club class of indiscernibles, so it is a club, it is closed and unbounded class of ordinals, C alpha, so that they generate L, and they are indiscernibles in the sense that for every increasing finite tuple, the L satisfies phi of C alpha 1 to alpha n, if and only if it satisfies C sub beta 1 to beta n. And so this is the class of silver indiscernibles. And in particular, this every uncountable cardinal belongs to one of those silver indiscernibles. And we may abstract a real number called zero sharp out of the silver indiscernibles. It is the join of n less than omega of first order formulas phi, which has n free variables and which are true of those silver indiscernibles in L. So this is a transcendental real over L that is called zero sharp. Itself can be a large cardinal axiom. So we would like to get a formulation of zero sharp in terms of well-founded remarkable EM blueprints. So zero sharp is the unique well-founded remarkable EM blueprint. So an EM blueprint is just a review. I think many of you are familiar with it. It is a complete consistent theory in the language of set theory plus omega many constant symbols, so that which contains the axioms CFC and V equals L, and the orders are C1 less than C2 less than C3, etc., and they are indiscernibles. There is a remarkability axiom which says it contains a certain remarkability axiom. So it is just a syntactical formula. It should be true in this EM blueprint. So from the EM blueprints, we are able to build the EM models. So for every linear ordering, there is up to isomorphism a unique model, which is generated by the points in this linear ordering, so that this is a model of the axioms when substituting those points. So this is a standard model theoretic theorem. This is called the M gamma less star is called the EM model associated to the EM blueprint. The EM blueprint is called well-founded, just in case for every countable well-ordering, the EM model comes out of this well-ordering is well-founded. And well-foundedness of an EM blueprint is pi1, 2. So it's a classical theorem that zero sharp is the unique well-founded remarkable EM blueprint, and we can relativize it to an arbitrary real number. So a uniform indiscernible means a silver indiscernible for L of x for every real number. And the uniform indiscernibles form a club class of ordinals. They are enumerated U alpha for alpha bigger than or equal to 1, the least one being omega 1, and the ordinal U omega draws our attention. This will be the least ordinals on which there is a tree effectively projecting to sigma 1 3 sets. So for now, this is the ordinal we want to look at, and there is a very natural way of coding ordinals up to U omega. So a sharp code is a pair of a Skolem term and X sharp, so that if tau is n-ary, then the tau evaluated in Lx on those indiscernibles is an ordinal, and this sharp code, well, it codes an ordinal in U omega by evaluating this Skolem term in Lx and plugging in those uniform indiscernibles. So this is, I guess, by Solovay that every ordinal in U omega is represented by a sharp code. The set of sharp codes is pi1, 2, and the relation that of two sharp codes being equal or less than is delta 1, 3. So this is the effective way of coding ordinals up to U omega. So the coding is by the sharp code. So here's the Martin-Solovay theorem that pi1, 2 sets is the projection of a tree on U omega, where the tree, well, it's coded as a subset of U omega, but every member of U omega is coded by a real number, so it is delta 1, 3 in terms of the sharp codes that codes the ordinals in U omega. And this is the optimal result about pi1, 2 or sigma 1, 3. And the tree is defined in terms of the Martin-Solovay tree. So for every order preserving map, it induces a map from uniform indiscernibles between uniform indiscernibles by well, you take a fixed Skolem term, but the arguments u1 up to um will be moved to sigma 1 of sigma m, where sigma is some fixed order preserving map, and every order preserving finite map induces a map in between the ordinals, and this definition is unambiguous. So this allows us to define the Martin-Solovay tree. We fix an effective list of Skolem terms, and tau n is k-n-ary Skolem term. So we have a recursive tree on omega on 2, so that the infinite branches is the set of remarkable EM blueprints over a real. So the remarkability is just a syntactical axiom, and being an EM blueprint is, well, it says it's a complete consistent theory, which is pi 0, 1, or so it can be represented by the infinite branches of a recursive tree. So T2, this is called the Martin-Solovay tree. It has two coordinates. The first one belongs to T, and the second coordinate alpha must try to validate that eventually the first coordinate must be a well-founded EM blueprint. So it's in the Martin-Solovay theorem that the projection of the Martin-Solovay tree equals exactly the set of X sharps, or exactly the set of well-founded remarkable EM blueprints. And Martin-Solovay uses the tree representation to get a basis theorem for sigma 1, 3 sets. So it is easy to define a variant of T2 so that the T2 hat will project to a good universal pi1, 2 set, well, just by making countably many copies of T2 and demanding that in the kth copy, the kth formula, the kth pi1, 2 formula must be true. So T2 is basically projects to a good universal pi1, 2 set. So let's recall that this is a tree on omega times u omega. It is delta 1, 3 in the sharp codes, and it projects to a good universal pi1, 2 set. So in the Q-theory paper, there is a definition of a particular real y0, 3. This is the leftmost real associated to the tree. So that's the first coordinate of the leftmost branch of T2. And here's the theorem that assuming large cardinals in the background, that then the leftmost real is many one equivalent to something called M1 sharp, which is the least mouse with a sharp above one wooden cardinal. So So the importance of this theorem is that, well, if you look at the definition of this real, well, it's defined out of the Martin-Soloway tree. It's just the leftmost real of a variant of the Martin-Soloway tree. And the Martin-Soloway tree comes from the EM blueprint formulation of sharps for reals. So this thing is something coming out of descriptive set theory and a little bit of inner model theory, namely the indiscernibles for the Gödel's constructible universe. Well, we look at the leftmost branch, and by the way, many one equivalence, it means Turing equivalence by acquiring only one value. And we look at the leftmost real, just all of a sudden, it is effectively equivalent to a mouse with a wooden cardinal. So it appears that we get a wooden cardinal out of sharps. The reason why it does not contradict Gödel's incompleteness is because we are assuming large cardinals in the background. So this is a strong justification of inner model theory. We spent so much energy on developing mice, on the fine structure, on the iterations, and well, it is just effectively equivalent to a real, which comes out of descriptive set theory mainly. So it's just connecting the descriptive set theory at the level of sharps to inner model theory at the level of one wooden and a sharp. So it appears that the wooden cardinals comes out of nowhere. So, also, by the way, so this I think almost 40 years ago, people proved the delta 1-3 equivalence of, I guess, of this thing at a mouse, or later with inner model theory, and this theorem just improves the delta 1-3 equivalence to many one equivalence. And to go further, we would like to define the projective ordinals. So delta 1n is the superlength of delta 1n pre-well orderings. And assuming large cardinals, they are strictly increasing. So the sup is smaller than theta L of R, which is smaller than the wage ordinal of universally bare sets. And we have the Susselin representation of certain levels of projective sets. And there is the Jackson's computation that, assuming AD, we get an exact we compute the exact position of those projective ordinals. So in particular, delta 1-3 is Aleph omega plus 1, assuming AD, and delta 1-5 is Aleph sub omega to omega plus 1. This is ordinal explanation, arithmetic. So, well, we can think of there are large cardinals in the background universe, and the theorem of this computation takes place in L of R. And at the even levels, we also have a Susselin representation, which is lambda to n plus 1 Susselin, where it is the predecessor of the projective ordinal. So under AD, the uniform indiscernibles are just the Aleph sequences up to omega. And we are able to code ordinals up to delta 1-3. This is because delta 1-3 is the successor of u omega, and there is a surjection from the reals onto the power set of u omega, assuming AD, and this surjection is effectively delta 1-3. So there is a canonical coding of ordinals in delta 1-3 by this generalized set, the generalization of WO, and this set is pi 1-3. So, well, we have answered the question of coding of ordinals, and also so we will get the Susselin representation of pi13 sets, but how to continue? So what is the next step after delta 13? So here is our big picture. So delta 11, delta 13, and delta 15, these are odd projective ordinals. And lambda 3 is the predecessor, and lambda 5 is the predecessor of delta 15, assuming AD. So let's see. So below omega 1, we have a coding of ordinals, countable ordinals in terms of orders of omega. And in this interval, this is in between aleph omega and aleph omega plus 1 in the AD world. They are coded by the Q-ness coding of subsets of U omega. So similarly, in the interval in between lambda 5 and delta 15 and so forth. So these are the odd levels of coding ordinals. So the blue color is the other coding, the other method of coding. So for the ordinals below U omega, we know that there is a sharp coding. It is a pair of a Skolem term and a sharp for a real. So ordinals in this interval has a canonical coding, which is a sharp coding. So it is very natural to ask that, well, is it possible to get a sharp coding up to the predecessor of delta 15? And also, it is a periodicity of order 2. So, and the purpose is of this talk is to carry out the sharp coding of ordinals in all those projective ordinals. So to continue the induction into the projective hierarchy, we would like to. It's necessary to develop the alternative formulation of pi 1 to n plus 1 sets. So this is a classical result in recursion theory that pi 1 is equivalent to sigma 1 over the least admissible set over X. And from that we can define the cleanness O, which is the collection of sigma 1 sentences true over the least admissible set. So O, it does not belong to L omega 1 ck, and it is in a sense the minimum one. So this picture generalizes to pi 13 by allowing an additional ordinal coordinate. So a subset of U omega times R is pi 13. So by the way, pi 13 means it is pi 13 in the sharp codes, because every ordinal in U omega has a sharp code. So it is pi 13 in the sharp codes is just equivalent to saying that there is a sigma 1 formula, so that X in A, if and only if this is the least admissible set containing T2X, satisfies that phi evaluated at T2, alpha, and X. So pi 13-ness is just sigma 1-ness over the least admissible containing T2 and X. Well, the point of adding this additional coordinate U omega is not for fun, it's for a fundamentally deep reason. So we can define the higher level analog of cleanness O, which has two coordinates. It's a pair. Well, the first one is the sigma 1 formula, and the second one is an ordinal in U omega. And it's the higher level cleanness O called OT2, which is the, well, it belongs to there, means the least T2 admissible set satisfies phi evaluated at alpha. So this is the correct generalization of cleanness O to the higher level. And the important fact is that this, well, as a subset of U omega, does not belong to the least T2 admissible, but every proper initial segment does belong to the least T2 admissible. So this object is a join of those countably many objects. And we define 0, 2 sharp. The nth piece of 0, 2 sharp. It is the set of pairs phi and c, which are obtained by applying a Boolean operation on the second coordinate of OT2 intersect omega times un. So it is a collection of pairs phi and c, so that we look at the least alpha where phi alpha does not belong to OT2 or psi alpha does not belong to OT2. It turns out that phi alpha, the phi side comes out first. So it is essentially a long Boolean operation acting on OT2 intersect omega times un. So this is how we define the nth piece of 0, 2 sharp, and 0, 2 sharp is the join of those pieces, and we can define the relativized version. Well, this is just the model theoretic definition of the leftmost branch of T2, which is called Y03 in the classical descriptive set theory. And so this is the model theoretic definition, and it is many one equivalent by the Kekros-Martin theorem. So eventually we get this 0, 2 sharp is many one equivalent to M1 sharp, and it relativizes to a real uniformly. So after all, this object is something that is definable over the least admissible set containing T2, and here is the definition. It is first order definable. The definition is slightly more complicated than sigma 1. It's a long Boolean combination of sigma 1 definitions, and it is effectively equivalent to something in inner model theory, which takes a lot of work to define. So and moreover, the equivalence is uniform. So having defined the level 2 sharps, we need the level 2 sharps to continue the induction onto the higher levels in the projective hierarchy. So for pi13 sets, there is a pi13 scale on the universal pi13 sets. So there is an object called T3, which is the tree of the scale, and the model LT3, this is an invariant model in descriptive set theory, in the sense that it does not depend on the choice of the scale or the universal pi13 set. So this object LT3 is a very canonical object in descriptive set theory, and it turns out to be a mouse. This is the local version of hard computation in the AD world. It is just a cut of an iterate of M2 sharp. It is a cut of M2 sharp at one of the strong cardinals up to the least wooden. And to continue the induction, we would like to analyze this structure LT3, but obviously, it is we lose a lot of information by cutting off the mouse M2 sharp. So to get back M2 sharp, the descriptive set theoretic way is to put in the level 3 indiscernibles into the structure LT3, and in the end, this will be equivalent, be bi-interpretable with M2 sharp, just as the theory of L with order indiscernibles will be equivalent to 0 sharp. So the point of defining the level 3 EM blueprints is that, well, just as how the level 1 EM blueprints are useful, they lead to effectively well-ordered cardinals and an effective coding system of ordinals in U omega and the Martin-Soloway tree, and eventually the descriptive set theoretic representation of the mouse M1 sharp. So similarly, we would like to have a similar scenario, and so we will have more effectively well-ordered cardinals of order type omega to omega to omega. This resembles Jackson's computation of delta 1,5. So there are a lot of structural theory on this weird-looking ordinal. And similarly, we have a delta 1,5 coding system of ordinals in this guy, which is the predecessor of delta 1,5. And we have the higher level Martin-Soloway tree, and we can continue the induction to eventually define the descriptive set theoretic representation of M3 sharp. So level 3 EM blueprint, well, it looks like it is the higher level analog of level 1 EM blueprints. So it is a function whose domain is the set of some technical term called the trees of uniform cofinality, and for every tree it is intended to be the theory of higher level indiscernibles. So gamma is a level 3 EM blueprint. It takes a tree of uniform indiscernibles to a complete consistent theory in the language of set theory plus finitely many constants, which contains a bunch of axioms that to make it look like the structure L delta 1,3 of T3. For example, it has V equals K, and I'm too small, and there are universally bare trees, universally bare class trees, which interpret sigma 1,3 sets in the correct way, and V is closed under M1 sharp operator as certified by the universally bare trees, and the higher level analog of the orders of those higher level indiscernibles. So, and similarly, we can define the EM level 3 EM model associated to this EM blueprint. And the blueprint must have the coherency property, which is the higher level analog of indiscernibility. So, in particular, they must cohere with each other, so that if R is a subfunction, then this EM model must embed into the bigger EM model elementarily in a unique way, and it contains the higher level analog of the remarkability property, which is purely syntactical, and finally a pi14 condition on the iterability property, which is the higher level analog of the pi12 property of well-foundedness of level 1 EM blueprint. So it is as if something is pi13 happens, then eventually the direct limit of the system of elementary embeddings between EM models is a pi13 iterable mouse. So just as the case with level 1 sharp, assuming pi13 determinacy, there is a unique iterable remarkable level 3 EM blueprint, which is the higher level analog of assuming pi11 determinacy. There is a unique well-founded remarkable level 1 EM blueprint, which is called 0 sharp. So we can define 0,3 sharp as the unique level 3 EM blueprint, and it relativizes to every real number. So in the end, the EM blueprint formulation is just many one effectively equivalent to the mouse M2 sharp. So this will be our descriptive set theoretic representation of the mouse M2 sharp X. So yeah, by the way, the proof uses the previous level, so it will be an inductive proof. And so just as we in one of the previous slides, we have those level 3 uniform indiscernibles of order type omega 2 omega 2 omega, and we have an effective coding system of ordinals, which is the higher level analog of effective coding system for ordinals in U omega. And we can similarly define the higher level Martin-Soloway tree, which was unknown. Well, only T2 was known, and we had no idea what should the ultimate effective version of level 4 Martin-Soloway tree should be. And finally, we have this. We can define the level 4 sharp. So this is the previous picture. So just now, what we did was this blue interval in between delta 1, 3 and the predecessor of delta 1, 5. All those ordinals are coded by the higher level sharp coding, namely a triple of this form. And this was the model theoretic form, which generalizes the level 2 picture by substituting this ordinal by U omega and T4 by T2, etc. And from this, we can define, in a similar way, the level 4 sharp as a set of formulas which takes the form of Boolean combinations of sigma 1, sets over the least admissible set over T2, and this will be the level 4 sharp, which is many one equivalent to M3 sharp. So our final picture is this zigzag picture. So it resembles Moskva-Vacas's periodicity of order 2. So we start from 0 sharp, and the next level is 0, 2 sharp, which is effectively equivalent to the mouse M1 sharp. And from this, we can prove the level 3 sharp as an EM blueprint. So the red colors are the theory of the mouse with higher level indiscernibles. They turn out to be effectively equivalent to mice with even number many wooden cardinals. And at the bottom level, so in the blue colors, we have the even levels of sharps, which are effectively equivalent to the mice with odd numbers of wooden cardinals. And they are truth values over the least admissible set over the higher level Martin-Soloway tree. So there is no reason to stop at the projective levels. So assuming large cardinals in the background, well, it should be possible to push this analysis in L of R and beyond as long as inner model theory is available. So what I mean is the colorful picture should continue to all the ordinals in theta L of R and beyond. And secondly is, well, this proof is really complicated. I must apologize that, well, the notes are still not available because there are too many details to check. But regardless of the details, they are the most natural things to do. So, and a possible simplification is, well, is it possible to avoid all the complications in Jackson's analysis, in particular the ordinal omega 2 omega 2 omega? So a test question is we should solve the fine structure of the least admissible set over T2, which is the tree on U omega. And finally, we can, as an application, we can prove the equivalence of light phase mouse M2M plus 1 sharp between the existence of this mouse and the determinacy of bold phase pi 1 to n plus 1 and light phase pi 1 to n plus 2 determinacy. So the proof generalizes the n equals 0 case, and the proof heavily relies on the equivalence of the descriptive set theoretic formulation and the inner model theoretic formulation of mice with wooden cardinals. And it is open whether for the even levels of mn sharps. So my big hope is that this this whole work will enable every theorem in descriptive set theory at the level of sigma 1 or pi 1 under the assumption of sharps for reals. Well, every such theorem should generalize to the projective levels under the assumption of PD. For instance, the classification of thin projective equivalence relations on R. So, well, every projective equivalence relation should either have a perfect set of mutually inequivalent members, or should have a nice well ordering, and the well ordering should have order type less than one of the projective ordinals. So, thank you for your attention.
Thank you very much. Question? John.
The last theorem, wasn't anti-Riemann involved in that? Or am I misreading it?
So, which one? This one?
Yeah.
This one?
That one, yeah.
This
For
one,
3.
well, for n equals 0, let's see. It is proved by maybe Itai Niemann and Wooden. Maybe I ignored.
So do these results shed some light on the question how to represent C3?
Yeah, that's a good question. Yeah, might be. There are some ideas on C3, but it's not directly. I mean, for C3, it's not directly connected to this result because there is the Martin-Solovay tree available. But for C5 and C7, we need this one.
Yeah. Other questions? If that's not the case, let's thank the speaker again.